All right, so we're going to look at now categories of functions here. This first one's called an injective function. It has several different names. It can be called a one-to-one function. It can be called an injunction or an injective function. And here's what it is, all right? Anybody want to try to read that?
Little a is equal to little b.
Very good. So for all possible values of a and all possible values of b, if f of a equals f of b, then a equals b. All right? So where's the a and the b coming from? Domain, codomain, where is that coming from? Just want to make sure we understand the formula here. They're all coming from the domain, right? This is like f of x subscript 1, f of x subscript 2, right? It's just every value of x, every value of a, but we just use a and b. So don't let that confuse you, because often when we're talking about little b, we're referring to the codomain. But I'm just saying, if I were to plug in some value a into my function, and it happened to equal whatever value I got back when I plugged in some value b, then that implies that a and b are the same thing. Okay, let's look at that graphically. One of those is a one-to-one function. One of them is not. What do you guys think? Right one's a one-to-one. Okay, and left one is not. Okay, let's see if you're right. Yes, okay. Now, here's what's going on. Notice, so let's just say f of a, we'll call this guy a, we'll call this guy b, right? Remember our formula down here, okay? I passed in a and I got whatever, some value 1. I passed in b, I also got the same value 1. So f of a is equal to f of b, agreed? But that's supposed to imply that a is equal to b, but they're not. That's a, that's b, they're different things, right? Each dot represents a different value. Dig it? Okay, over here, f of a is equal to this, f of b is equal to that, f of c is equal to that. So this never even happens. There's never a case where f of a equals f of b, which means this is vacuously true, right? Because the first thing, the p, never happened, and therefore the q doesn't matter, right? Feeling okay about that idea? That's a one-to-one function, okay? You can graphically represent these, and you can tell if it's a one-to-one function by using the horizontal line test, okay? One of these is a one-to-one function, one of them is not. Any guesses?
Left
Is?
1-to-1.
He says the left is one-to-one and the right is not. I'll buy that. And a vertical line test says if you draw a, horizontal line, if you draw a horizontal line through it and you cross 2 points or more, then it is not a one-to-one, okay? That just means it's simply a one-to-one relation from the left to, from set A to set B, all right? To the whiteboards. Okay, so the answers we want to see if these are one-to-one functions, all right? A rule is for all A and all B, and again, A and B are just placeholders for the 8th value in the set and the bth value in the set, right? They're just placeholders. So if I were to grab some random value out of the set A, which is A, B, C, D there, and I would grab some other random value, if they were equal to each other when I plugged them into the function, then that would mean A is equal to B. So what's the answer we got for the first one? Oh, sorry, I revealed it too soon. Okay, why is it true? Everybody got true, I think. Why is it true? How did you come to that conclusion?
First set, one has one.
Yeah, it's vacuously true, right? Because there's no case where f of a and f of b or f of x1 and f of x2 or whatever you want to call it are equal to each other. So therefore, the left side of our p, therefore q, never even occurred. So it's vacuously true, right? Each value of in the domain maps to a different value in the codomain, and there's no case where they equal to each other, okay? All right, next one, we got false. Why is the next one false? I think everybody got that correct as well. How do we prove that?
Plug in plus or minus 1.
What do we call that? Proof by? Counterexample, not contradiction, proof by counterexample. Yeah, proof by counterexample. So we found a counterexample, which was if we plugged in 1 and -1, we would still get 1. Well, that's a problem, because remember, the rule is if I plug in some number here, we'll call it A, and some number here, and they equal each other, which they do, if they equal each other, then that means that A equals B. But clearly, A does not equal B. So that is a problem, okay? So proof by counterexample, very good. Next one is true. This one's a little trickier, okay? How do we know it's true? Because we're dealing with an infinite set of numbers here. And we're dealing with different infinities even, right? Because real numbers are decimals and everything included. Well, there's an infinite number of numbers between 1 and 2, right? There's 1.1, 1.11, 1.12, up to infinity numbers of things after the decimal place before I even get to the number 2. So we're talking like huge infinities here. How can we prove that that's true? How do we know? There's a technique, an official technique, but you guys kind of did it intuitively. We'll learn the technique later. It's called mathematical induction, okay? The way we know it's true is this. X plus 1 is not equal to y plus 1 when x is not equal to y, right? What the heck does that mean? Okay, oh, oops, let me do that. What does that mean? Well, think about the values I plug in here, okay? If I plug in an x here, I'm going to get whatever I started with plus 1 value, okay? Well, what's the next thing I could plug in for x? I could plug in x plus 1 for my next x, and that'll give me my previous 1 plus 1 more. Well, I'm basically just adding 1 to everything, right? So there's no scenario where if I take a number and add 1 to it, that I'll get the same output as the previous number, because I've added 1 to it, right? There's just no way. Okay, hopefully that's clear. If that's a little fuzzy, double check, read the book. I like to solidify it. Read the book, chapter 2.3, I think this is, okay? All right, but that one's also true, okay? So any questions about this? Good? All right, we're going to cruise through. Next kind of functions, surjective functions. If we had more time, I'd have we do these on the whiteboard. But there's some other names for these. It's called an OnetoOne function, or a surjective function, or a surjection. Okay, those are all names that work for this. And here is our function for that, our formula. Andrew, you want to give a shot at that, reading that?
Let's see, for all y, there exists one x such that f of x equals y.
Very good. So at least one x, but other than that, correct. For all y, there exists at least one x such that f of x is equal to y. Okay? So what does this mean? In this case, we're specifically saying that x is the domain and y is the codomain, right? Where before everything was coming from the domain. What does this mean?
Does that mean there's an input for every output?
Yeah, that's exactly what that means. There's an input for every output. In other words, every value in the codomain will be reached if you plug in all the values from the domain. Okay? We had that happen a minute ago, right, with the binary thing. That was an onto or surjective function. Okay? All outputs will be reached. In other words, the range is equal to the codomain. Whenever that happens, you have what's called an onto function. So one of these is a surjective function, one of them is not. I know you kind of saw the answer there, but maybe you didn't happen to notice. Which one is a surjective or an onto or a surjection, and which one is not? And why? Say again?
The second one is
The second one is, why is that?
every possible thing for a domain gets reached.
Yeah, so the domain is and the range are the same, right? Again, here the domain is this. Or the codomain, I should say, is this. The range, however, is only this, right? So not every value has been reached. Over here, the codomain is this, but so is the range, right? It's all of those were reached, okay? All right, how do we feel about that? Again, you can represent these on a graph. One of those is an onto, one of those is not. And this is what the difference between what they look like on a graph. They could look like this, right? Okay, and again, these pictures are in the book, I'm pretty sure. I think, could be wrong, but if not, they're in the video. You got them. So the question would be, if I have a function from a, b, c, d to 1, 2, 3, and then those are the values, f of a equals 3 and so forth, And then the next one, integers to integers, f of x is x squared, and integers to integers, f of x is x plus 1. Which of those, if any, are ontos or not? Any thoughts?
One's only on two.
All of them are on two.
All of them are onto is one answer. What's another one I heard?
All of them are on two except for two.
Except for number 2. So true, false, true. Okay, here's our formula. For every y, there exists an x such that f of x is equal to y. Okay, the first one is true. How do we know that? That's easy to see, right? Because that's our codomain, right? And did 1, 2, and 3 get hit? Yeah, they sure did. All of them got hit. Range is equal to codomain. Good? Okay? All the outcomes were reached. Second one is false. Why is it false? And again, counterexample, all negative numbers, right, would not be reached. The whole entire less than 0 would not be reached. So there's no such thing as x squared equals negative 1, in other words, right? Last one is true. And how do we know it's true? Would all numbers be reached? That's an iffy one, right? Because no, but yes, right? Because it's infinity. You can't reach infinity. You can only approach it, right? And no matter how much you approach it, you're always kind of the same distance away from it, right? But in theory, yeah, there's always plus 1. You can always get to whatever that range of those numbers you can get to them, yeah, okay? For all numbers in codomain, f of x exists, right? Every number in the codomain, which is all integers, there is some number that I can add 1 to and get it, right? Okay, bijective functions. What do you suppose a bijective function is?
Injective and surjective.
Yeah, exactly right. It's one-to-one. It's called a one-to-one correspondence. It's called a bijection, bijective function, and it's both one-to-one and on-two. Okay, very good. So here are 5 examples here. What I want to know is what type are they? So let's look at them one at a time here, okay? What type of function is that? Is it a one-to-one, an onto, or both, or neither? What is it? Surjective? What's the other name for surjective? Onto. It is an onto only. Why is it not a one-to-one? Remember, on a one-to-one, if f of a and f of b match each other, then a does equal b. And again, each dot does represent a different value, right, in this case, okay? All right, good. Next one. What do we got here? Okay, all outcomes were not reached, and we also have a scenario where the same values, where we have 2 inputs going to the same output, right? So correct, neither. Okay, next one. Not a function. Very good observation. Why is it not a function? Yeah, this guy right here is our problem, okay? This guy has 2 different outputs, therefore he's not a function. And by the way, just to point out over here, we were talking about on this one, the problem we had was that this guy and this guy, sorry, no, let me undo that. This guy and this guy both went to here. Remember, if f of a, whatever it equals, and f of b equals the same thing, then that means a is b and a is not b here. That's why this is neither. And then again, over here, the problem is 1 input, 2 outputs, making it not a function, okay? And then the next one, what's this one? Bijective. All outputs are reached, and it looks like each input has a different output. They're not equal to each other, so it's vacuously a one-to-one, right? Okay. Both. Last one. What do we got? It's a one-to-one, but not an on-to, because not all values were reached. Okay. It's a one-to-one only. Looks like you guys feel okay with that. We feeling all right? Yeah. All right, so now this is a big topic, and we got about 15 minutes to briefly cover it. When you have a relation on itself, right, a relation on A is what we call that, there are some interesting properties that we can discover. So let's start with, we'll let A be the set 1, 2, 3, 4. What ordered pairs are in the following relation? A comma B, where A such that A divides B. What does that even mean, A divides B? It just can be divided into it, right? Just evenly divides into it, right? So, for example, I'll just give you some examples here. You can see it. The relation would be 1, 1, 1, 2, right? Can 1 divide into 2? 1 can go into 3, 1 can go into 4. 2 can go into 2, 2 can go into 4, 3 can go into 3, 4 can go into 4, right? That's what that means, A divides B. So the number on the left here, A, right, we'll just pick this one, can be divided into B, right? A is dividing B, right? In other words, A is dividing, so 2 is dividing 4 into 2 things, right? So that's that's an answer to it. But there's some properties that we can see that we will look at in just a minute. But I wanted to show you this idea that oftentimes when you have a relation, you're given some sort of a rule like this, where what is a relation such where A comma B such that A divides B, okay? Lots of different rules, and we'll look at a few examples here in just a second, okay? For these right here, in fact, okay? So which relations below contain, that should say any of the ordered pairs there, 1, 1, 1, 2, 2, 1, 1, negative 1, or 2, 2. So if I were to calculate all of the ordered pairs that I could get from the relation A comma B such that, in this first case, A is less than or equal to B, where would any of these show up? Or in this case, where A is greater than B, so on and so forth, assuming that we're using the integers, right, as the domain. Where would each of these go? So where would 1 comma 1 go?
R1.
Okay, we go in R1, we say. Where else? If anywhere else.
R4.
R3, R4. And R6. Yep. 1, 3, 4, 6. Okay. What about 1, 2? Where would that go?
R1.
Okay, R1, anywhere else? 4? 5, okay. Anywhere else? Just 1 and 6. Why would it not go in 5? Yeah, good. Okay. All right. What about 2 comma 1?
Then it would go 5.
2 comma 1 could go in 5, we said. Where else?
Go to 2.
Could go to 2. Anywhere else? 2, 5, and 6. Do you see what's happening there? What about 1, negative 1? There you go, 2, 3, and 6. Okay. And the last one, 2 and 2, I'll just put it up there for you. All the light blue ones there. All right. So there, if we're using the set of all integers, this could be obviously way more answers, but those are legitimate things that could be there. So I just want to show you that briefly so you understand the idea of how is a relation created, right? Remember, all relations are a subset of the Cartesian product. So what's the Cartesian product of a relation of integers on itself? It's infinite set, right? It's huge, okay? So this is just a subset of that. It's some calculation that says anytime A is less than or equal to B, put it in the set. What you see on the screen is not the complete set that you would have, obviously, because the integer set is humongous, all right? So let's look at some of these common properties here, and this is where it gets interesting, and when we dive into matrices later and some other things in the future, we'll see this more. We have what's known as a reflexive property. For all A, the pair A comma A is an element of the relation. So when I make my relation, the A comma A will be an element of that relation. So if my original domain is 1, 2, 3, 4, then what must exist in my relation for it to be reflexive? 1, 1, 2, 2, 3, 3, 4, 4. Very good. Whoever said that. Who said that? Oh, good. Good. Another ventriloquist over there. Okay? Yeah, very good. Okay, and we'll look at examples in a minute. Okay, symmetric. For all A and all B, if A comma B is an element of the relation, therefore B comma A must also be an element of the relation. In other words, if there's a 1 comma 2, there better be a 2 comma 1. Right? If there isn't a 1 comma 2, then there doesn't have to be a 2 comma 1. Okay? It would vacuously still hold and be symmetric. All right? Antisymmetric. Look at this messy thing here. Let's test our knowledge about reading this stuff. For all A and for all B, if AB is an element of the relation and BA is an element of the relation, therefore A is equal to B. All right? So what this means, if A and B and A are the same, that means we have like a 1, 1, right? That means they're equal to each other. A and B are equal to each other. And we'll see examples in a minute, okay? Last one, transitive. This is a lot simpler than it looks. We know this one. This is basically the old idea that if x equals y and y equals z, then x equals z. That's the basic idea, right? So for all A and all B and all C, if A comma B is an element of the relation and B comma C is an element of the relation, then A comma C should be an element of the relation, right? So in other words, we have AB, BC, right? Then that means there needs to be an AC, right? That right there. Do you see the transitive nature of that? Does that make sense? Okay. Why do we care about transitive and reflexive and symmetric and antisymmetric? And there's other ones like anti-reflexive and a bunch of other ones. Why do we care about these? These are just words to describe the nature of something, right? Your shirt is blue. This table is white. This chair is black. This matrix, this relation is reflexive. They're just adjectives to describe them so that when we speak about them, we have a vernacular that we can use, okay? That's all it is. To the whiteboards. We have set A, we're going to do a relation on itself with the relation where A divides B, or A is less than or equal to B, or A is greater than B, or A is equal to B. Are they reflexive, symmetric, antisymmetric? What are they, if anything? So here's the sets that we would get, right? Would you agree that those are the sets there? Okay? If A divided B, I'd get 1, 1, 1, 2, so on and so forth. Those are the sets. So looking at those sets there, is it reflexive? Is there a 1, 1, a 2, 2, a 3, 3, and a 4, 4? Is it reflexive? Yes. The first set there? Yeah. Is it symmetric? In other words, if there's an AB that's in the relation, then there should be a BA. Let's just briefly look at that, and we won't walk through this on all of them, but let's just take a look. Okay, an AB, all right? So I have an AB that's a 1, 2. That means there needs to be a 2, 1. And there's not a 2, 1. Okay, so it's not symmetric. All right, how about antisymmetric? Well, that is if A and B is a relation and B and A is a relation, then that means A equals B. Is it antisymmetric? Yep. It actually is. Because A, B exists, and so does BA, right? It's the same thing, but it does exist, right? And therefore they're equal to each other. That's what antisymmetry is. You dig it? I see a couple puzzled looks. Okay? So let's look at this rule again. If A and B is an element, or A comma B is, and B comma A is an element, if that exists, does that exist? Here's an AB, right? Remember, AB is just, we call the first thing A and we call the second thing B. It doesn't matter what they are. That's AB, right? 1, 1. Is there also a BA? 1, 1, right? So the first part is true. If this is true, therefore this is true. Well, is A equal to B? It is, right? 1 is equal to 1. Make sense?
Reflexive the same as that.
Not necessarily, because the question was, is reflexive and antisymmetric the same? The answer is no, because let's just pick one. If 4, 4 was not here, it would still be antisymmetric, but it would not be reflexive. Because when it's reflexive, it has to have all of these paired with themselves, right? It has to have 1, 1, 2, 2, 3, 3, 4, 4. But to be reflexive, or to be antisymmetric, first of all, it could have none of those 1, 1s, 2, 2s, 3, 3s, 4, 4s, and still be antisymmetric, right? Because then it would be vacuously antisymmetric, because the first condition is met. But even if it's not vacuously antisymmetric, and we're just missing some of the stuff that makes it reflexive, it could still be antisymmetric. Yep. Okay, tricky. Another thing to keep in mind when you're talking about the antisymmetric property is if we have a scenario like, for example, we have 1, 2, and then let's say we also had 2, 1. Well, let's look at the rules of antisymmetric. We have A comma B, which is 1 comma 2, and then we have B comma A, which is 2 comma 1. So let's just make this more clear here what I'm saying. If I have this in the pair, and I also have, or in the set I should say, in the relation. So if I have these two here like this, if I have 1 comma 2, or in other words, A comma B, and I also have 2 comma 1, then look at the last part of the relationship here. If I have AB in the relationship and BA in the relationship, then A equals B, right? Well, look at our picture here. Does A, right here, does A equal B? And it does not, right? So again, just to be clear, this example here, if A comma B is, I'm going to just put a little E here, is an element of the relationship, and we're going to go with and, since I can't write symbols in Notepad here, and B comma A is in the relationship, therefore A is equal to B. That's the rule, right? Okay, that's kind of weird to type it this way in Notepad, but that's the basic rule. So look at what's going on here. Where's the A? Well, it's the 1, right? A is just whatever the first number is in your set, in your ordered pair. Where's B? Well, B is the second number. Okay, so I do have an AB. I mean, any pair is an AB. Even if there's only one ordered pair, it's still AB. All right, well, I have AB, and that's in a relation. That's in our relation. Is BA in our relation? Yes, BA. In other words, if I reversed my AB here, I would get that. And is that in a relation? Yes, that is. This whole thing is true. Therefore, this has to be true, but it is not. Therefore, in this scenario, it would not be antisymmetric. But in our case, there's no scenario where if I have an AB and a BA, where they're not equal to each other, right? So take a look at these pairs here. I have 1, 1, and if 1, 1 is A comma B, well, what's B comma A? Well, it's also 1, 1, right? So in that scenario, just with this ordered pair right here, well, I have an AB, which is an element of the relation, and I have a BA, which is the element of the relation, which is also 1, 1, right? So, and in that case, is A equal to B? Yes, it is. Okay. Well, let's look at the next one here. 1, 2. If I look at 1, 2, the next question is, do I have a 2, 1? Right? 1 is A, and 2 is B, right? And do I have a BA? In other words, do I have a 2, 1 anywhere? And I do not have a 2, 1 anywhere in here. So in that case, this part is true, but this part is not. Right? As long as you have ordered pairs, the first part will always be true. This little piece right here, there's always A comma B, because that's just randomly any pair, right? Any ordered pair. But the second part is not true, which means that the hypothesis of our P therefore Q, our conditional statement, is false. Well, if this is false, then this value is irrelevant, right? That's what we call vacuously true, right? So let's look at the next one. 1 comma 3, that's our A and B. A is 1, B is 3. Is there a B comma A? In other words, is there a 3 comma 1? And there is not. So again, this is vacuously true. All right, there is a 1, 4, that's our AB. Is there a 4, 1? No. So again, this part's true, but this part is not. Therefore, the part that's on the left of our conditional arrow is false. Therefore, it is vacuously true. Right? Again, now we have a 2, 2. Okay? So here's 2, 2. Well, our A is there and our B is there. Well, do I have a BA? Well, I do. It's 2, 2. It's the same thing. It's itself. So in that particular case, it is antisymmetric. Next one, we have a 2, 4. Do I also have a 4, 2? And I do not. So it's vacuously true. I have a 3, 3, which is my A comma B. Do I also have a B comma A, which is also 3, 3? And obviously I do. And the exact same thing will happen with the 4, 4. So that's how it works for antisymmetric. You have to check every ordered pair for all of these properties to make sure that it pans out all the way across the entire set. Is it transitive? Okay, that one takes a little bit more time to walk through. So let me briefly just tell you. The idea is there's a 1 comma 2 here, and now is there a 2 comma something else? Like there's a 2 comma 4 here, then that means there needs to be a 1 comma 4. Follow that? Right? Now you have to do that with all the sets to make sure, all the pairs to make sure it pans out completely across, but you will find in this case it does, okay? So let's look at the answers here real quick. And it is antisymmetric, transitive, and reflexive, but it's not symmetric. Okay? I want you to, I'm just going to show you the answers right now. walk through this and pause the video and try this out, okay? The next set is the same. It's anti-reflexive, transitive, and reflexive, or anti-symmetry, I meant. This one is anti-symmetric and transitive. The last one is all of them. You can be anti-symmetric and symmetric at the same time. That is available. That is a possibility. How can you be symmetric and anti-symmetric? Well, let's take a look real quick. Clearly, it's reflexive, right? 1, 1, 2, 2, 3, they're all there, right? Is it symmetric? Well, if A comma B is an element of the relation, then B comma A is. Well, is that true? Yeah, 1, 1's there, therefore 1, 1 needs to be there. Yep, right? 2, 2, therefore 2, 2. Is it antisymmetric? Yeah, every time you do have a 1, 1 and every time you have a symmetric pair, are they equal to each other? Is A and B equal? And they are. And it's transitive because, again, the idea of transitive is, since there's a 1 comma 1, I need to look for anything else that starts with a 1. Well, nothing else starts with a 1. But if it did, if something else started with a 1 and then there was another value, I have to have a connection between the two. But there is no case, so this one just vacuously is true. Okay? So it can be all of them. To the whiteboards. We have set A is 1, 2, 3, 4, and we're going to do a relation on itself. In other words, a relation on A, right, from A to A. And when all was said and done, whatever the rules of the relation were gave us as a result this for one set of rules, or another time it gave us this. And you'll remember a few slides back we talked about how we might describe a relation where give me A comma B such that A is less than B or something like that. Some rules were used to create each one of these relations. What the rules are, how we got these relations is irrelevant, but just what we're looking at is multiple relations here. This is the first one that we did, and then somehow we come up with another relation and so forth. So we have a total of 1, 2, 3, 4, 5, 6 relations here, and each relation has a set of ordered pairs in it. The question you're going to answer is this relation reflexive? Is it symmetric? Is it antisymmetric? Is it transitive? And of course the rules are down here to help you remember. And then is this one reflexive, symmetric, and all the way down? So do all 6 of those, and then we'll talk about the answers in just a moment. Okay, we'll walk through the answers to these in just a moment, but for now, here's another set to do the exact same thing. Pause the video, take a look at these problems right here, and see if you can come up with the answers of what properties they hold. Well, let's start by looking at this one here and seeing what the answers to this second set of problems will be, and then we'll go back and look at the first set. All right? So here we go. These are the correct answers, so go ahead and take a look and see if they match up with what you got, and then let's sort of walk through each one of these and see how we came to this conclusion. Let's first take a look at the ones that are reflexive. There's just 2 of them that actually have the reflexive property here. So let's take a look at how these play out. What makes it reflexive? Simply if for all, now this is important here, for all A, the pair AA exists. Well, what is A? What is this little a here when we're talking about for all A? Well, that's, the little a is representative of the set big A, right? We just are using variables to talk about what's in the actual set. If this set were called B, then we would be using a little b to represent it, right? You can use anything, but the idea is we're talking about for all elements in the set. So for this element as A, is there an A comma A? In other words, a 1 comma 1. For this element in the set, is there a 2 comma 2? Is there a 3 comma 3, 4 comma 4? That's what we're asking here. So if we look here, this one, it clearly has, for that A, 1, there's a 1, 1, there is a 2, 2, there's a 3, 3, and there's a 4, 4. So it's clearly reflexive. This one as well, in fact, that's the only thing in the relation is the 1, 1, 2, 2, 3, 3, 4, 4. So that makes both of those reflexive. Why is this one not reflexive? Well, because it's missing a 1, 1 and a 4, 4, it looks like. So it's got the 2, 2 and the 3, 3, but it does not have a 4, 4. So I think reflexive is pretty easy to spot. I don't think that's too confusing. Well, how about symmetric? There are 3 of them that have the symmetric property, right? So this one, and this one, and this one. Let's start with this middle one here because it's pretty easy to see the symmetric property here. Look at the rule here. For all A and all B, and again, this A and B is just ways to represent the stuff that's coming from the set, okay? Ultimately, when we do this relation on itself, when all is said and done, we're going to have a whole bunch of ordered pairs. In this case, we had 6 ordered pairs. In this case, there's only 2 ordered pairs, right? And so we're going to have a whole bunch of ordered pairs, and we're going to represent them with just generic variables, A and B. So we're simply saying that for every single A, when it's positioned here in the first part of the parenthesis, the x coordinate, if you will, in an xy pair, right? So if it's for every A that's positioned here, and then for every B that's positioned here, and notice where, because this is a conditional, how do we read conditionals? We say, if this, therefore this, right? That's how you read the P, therefore Q, or the conditional style statement. So again, the idea is for every single A and every single B, if there's an A comma B, then in the relation, an element of the relation, therefore there must be a B comma A as an element of the relation. So looking at one that has the symmetric property right here, actually we're going to start with this one because it's easier, it's smaller. Here's my A, 2, and there's my B, 4. There's a 2, 4. That means, therefore, there must be a 4 comma 2 for it to be symmetric. Sure enough, there is, right? Now, since there's only 2 ordered pairs, we're done. We don't have to look any further. But just to sort of overstate the obvious here, here's the other pair. It has A is 4, B is 2, so that's A comma B, 4 comma 2. Is there also a reverse of that, B comma A, which would be 2 comma 4, and obviously it's just right there. So that's that one. Let's look at another one that's symmetric here. And again, this is easy to spot since we're only dealing with the reflexive, this is a reflexive set here that has just 1, 1, 2, 2, 3, 3, and 4, 4. Well, there's my A, there's my B. That's A comma B, 1 comma 1. If I have a 1, 1, do I also have a reverse of that, which also happens to be 1, 1? So obviously I do, okay? And that will hold true for the 2, 2, the 3, 3, and the 4, 4. So those two are pretty easy to spot. Let's look at this last one here and make sure that we also see it, okay? So we have a 1, 1. That's our A and our B. Do we have a BA? Well, yeah, that's just a 1, 1. Okay, fine. Here's a 1, 2. That's our A. That's our B. Well, if there's an AB, do we also have a BA, which would be a 2, 1? And sure enough, there is a 2, 1 right there. So that's pretty straightforward. Next up, I have a 2, 2. Do I also have a 2, 2? Obviously. Same with 3, 3, 4, 4. I have an AB, and the BA just happens to be exactly the same. So this one's pretty easy to spot it, right? Let's look at one that's not symmetric so we can see why it isn't. So looking here, if I only looked at 2, 2, so far it's symmetric, right? Because I have a 2, 2, that's my AB, and I reverse it, that's my BA, it's there, right? Well, look here, I've got a 2, 3. If there's a 2, 3, an AB, then there needs to be a BA. Well, what would be BA? It'd be 3, 2. Do I have that? Yes, I do. So far, so good, right? Let's take a look at the next pair. 2, 4. That's my A, that's my B. If I have a 2, 4, I also need to have a B, A, which is a 4, 2, and I do not have a 4, 2. Therefore, it is not symmetric. Because the problem is, this was true, but this was not. And remember, in a conditional, if the hypothesis, or the P, or the thing on the left of the arrow, is true, then the thing on the right of the arrow must be true for the whole thing to evaluate to true. And we have a true condition here, which is our 2, 4, but a false condition here, which is there is no 4, 2. That's why it is not symmetric. So I think we're okay on those. Let's take a look at antisymmetric next. So only 2 of those were antisymmetric. That was this one and this one. So let's see why they are antisymmetric. Remember, the rule is if A, B is an element of the relation, and BA is an element of the relation, then A must equal B. Okay, well, let's look right here. let's start with, let's look at this one. We saw this one already on the, a couple slides ago, I think, where we see there's a 1, 1, and so I'm asking, is there A, B? So we're calling the first thing A, the second thing B. Okay, is that true? Yeah, it is. Okay, is there also a B comma A? Well, I'm going to flip that and I'm going to get B comma A, which would also be 1, 1. Okay, so in that scenario, then this part is true and this part is true. Therefore, my hypothesis, the thing to the left of the arrow, is true. Therefore, the thing to the right of the arrow must be true for this whole thing to be true. Well, the thing to the right of the arrow is A equals B, and that is true, right? And this will hold for 2, 2, 3, 3, 4, 4. That one's, it's pretty easy, pretty straightforward, okay? We looked at that a few slides ago. The next one, this one's a little bit trickier. It's not hard, but let's just take a look at it. What we're saying here is, remember the question we're asking. For every scenario, all A, all B, where A, B is an element of the relation, and that same BA is an element of the relation as a pair that's, you know, backwards from this one, A, B, BA. Every time there's both of those, then the A and the B must equal each other. Okay, well, let's see if we have this. We have a 1, 2. Do I also have a 2, 1? Right? I have this, AB is an element. Do I also have BA? And I do not. So that means that the thing to the left of this little conditional arrow, my hypothesis, is false. Therefore, this is, so far, we're not done yet, but so far, it is vacuously antisymmetric, right? Let's look at the next one, 2, 3. Well, I have 2, 3, the AB. Do I also have BA? 3, 2. I do not have BA. So in this scenario, I do not have AB and I do not have B. I have AB, but I don't have BA, which means, again, this one is vacuously still antisymmetric. Now, we haven't looked at the last element. Maybe that would change things, but let's take a look. And I now have a 3, 4. That's my A, B. That's the first part right here. Do I also have a BA? Do I also have a 4, 3? And I do not. Okay, if I did, then A would have to equal B, and since 4 does not equal 3, we'd have a problem. But since the hypothesis is never true in this scenario for this particular relation, then it is vacuously antisymmetric. Let's take a look now at the transitive property, the 3 relations that have the transitive property. This will be a little bit trickier. What I've done on the next slide is I've just removed all of the relations that do not have the transitive property, so we can just focus strictly on transitive, because this takes a little bit more explanation to make sure we fully understand it. Let's again make sure we understand the rule here, right? What is the rule? Well, we're now talking about 3 variables, right? And again, these are just variables that are going to represent something inside of here, right? And those variables are A, B, and C. And we're saying for every scenario where we talk about an A or a B or a C, that if AB is an element of the relation, and BC is an element, and who knows what A, B, and C are, but if this is such a thing and this is such a thing, if both of those exist in the relationship, or in the relation, I should say, then AC must also be an element of the relation. So let's take a look at an actual example here with the first one that we're going to look at, and that's this top one. I just moved it over to here, okay? So let's take a look at this piece at a time. Is there an AB and a BC, right? Remember, that's what we're asking here. We're saying AB, BC, right? Do we have an AB and a BC? Well, you always have an AB, right? Even if there's just one pair in the relation, it is the AB. The reason it's the AB is because we're just assigning arbitrary variables to say we will use A to represent the first number in the pair and B to represent the second number. So even if this entire relation only consisted of that pair, well, we still have the AB. A is whatever's on the left of the comma, B is on whatever's on the right. So you'll always have an AB if there's something in the relation, okay? But the next question is, okay, do I have a BC? Well, what does a BC look like? Well, if this is AB, and we're going to have to look at every single pair to check this. If this is AB right here, well, I'm looking for B something that starts, so here's the B, where I'm looking for something that starts with a B and then has some other value. Okay, well, are there anything else here that starts with a B? And in our case, B is equal to 2. Well, yeah, this starts with a B, that starts with a B, right? And again, B just at the moment is the number 2. Well, so we do have a BC, right? Here's our B right here, and there's our C. Here's another B and another C. So yes, B and C definitely do exist, all right? So there's a 2 comma 2. In other words, is there a 2 comma C, right? And just to be clear, this 2 is that 2, right? Because we're talking about this B and this B. That's the same B, right? So the transitive property is going to go eventually, as we see this A to C right here, we're going to make a connection from this to this. That's the hope, if it's going to be transitive, all right? So again, we have an AB and a BC. We've shown that, right? There's a 2 comma 2. Is there also a 2 comma something? And yes, we have two comma somethings, right? Okay. All right. So that means we must have an A comma C, right? Well, let's go back to these numbers again. Make sure we know what the A comma C would be. What's our A? Well, our A happens to be the number 2 again, right? This is the very first pair we're looking at. It happens to be a 2. So I need a 2 comma C. Well, what is C? Well, it's 3 and it's 4. So that means I need to exist a 2 comma 3, and I also need to exist a 2 comma 4. And we do. It just so happens those are ones that are in play with this particular, they're also part of the B comma C, if that makes any sense. Right? We'll see a different scenario in just a few minutes. So hopefully that makes some sense. Again, the basic idea is this. We're looking at every pair. We're going to do this for all the pairs here. And I'm looking at the pairs, and I see there's my A, there's my B. Now, do I have, that's my AB, okay? Remember, is there an AB in the relation, okay? Now that I do have an AB, is there a B something else, a B comma something else? Well, what's the B? Well, it's the second letter. It's this thing right here, okay? Is there something that starts with this and ends with something else? Well, yeah, there's something that starts with 2 and ends with something else. There's a 2 that starts with 2 and ends with a 3. There's a thing that starts with 2 and ends with a 4. Okay, so is there this? Yeah, in fact, there's 2 of those. Well, for each one of those, so we now have this pair 2, 2, and 2, 3. Therefore, there better be a 2, 4. Or sorry, excuse me, a 2, 3. Okay, now it seems a little redundant because one of these, the BC, is the 2, 3. Well, the 2, 3, BC is also the AC in this situation. Okay, the same thing will pan out with this 2, 4. Let's take a look at another one though. That's not as, this one's maybe a little confusing sometimes when you're dealing with the same set of numbers, the same pair as being both the BC and the AC. Right, we're going to see that a couple more times, but we're also going to see somewhere that's not how it plays out, but it still is going to be transitive. All right, so we have the AC, which they exist. We're good there. Okay, do we have, yes, do those exist? And they do, okay. All right, let's take a look at the next set here. So clearly 2 comma 2, when checking that, so far we are transitive, but we still have 5 more pairs to check, all right? So let's check the next one. We have the AB. We will always have the AB, right? What is the AB in this particular case? Well, it's 2 comma 3, right? We're looking again, we're just looking at this pair now, and we're saying, okay, that's our AB, right? So A comma B, 2, 3. Do we also have a BC? Well, what's B? It's this number here, right? It's this number here. Do we have something that starts with that, and ends with something else? So do we have a 3 comma something, a 3 comma C? Do we have that? And as you can see, the answer is yes, we have 3 of those. There's a 3 comma 2, a 3 comma 3, and a 3 comma 4. Each one of these is the B comma C, right, in this particular scenario. So I started off with this pair. That's my AB. Now I'm looking for any BCs. In other words, anything that starts with the thing that this ended with. Well, what did it end with? It ended with 3. Do I have anything that starts with 3? I sure do. I got 3 of them. 1, 2, 3 right there. Okay, if I have 3 of those, then if I have those, what do I also need? Well, I need now an A, comma, C. Well, what's my A? It's 2. And then I need a comma C. Well, what are all the C's? That's a C, that's a C, that's a C. So in other words, I need an A, comma 2, or a 2, comma 2. I also need a 2, comma 3, and I need a 2, comma 4, right? So taking a look at this, do we have the AC? As I've pointed out, we need to have these. We need a 2, 2, a 2, 3, and a 2, 4. Let's make sure that's clear. Again, I know I'm beating a dead horse here, but it's important that we really wrap our heads around this. This is a tricky concept at first. The idea is this. Again, we're taking this pair, we're calling that A, that B. There it is. Do we have an A, B in the relation? Yep, we do. Do we have a B, C? In other words, do we have something that starts with our B, which is 3 in this case, and has some other number after it? So how many 3 comma somethings do we have? We have those ones right there in purple. Great. So the next question is now, do we have whatever our A was, 2, right? Whatever our A was, comma, whatever our C was. Well, what are our C's? They are 2, 3, 4. Okay, so that means we need a 2, comma 2, a 2, comma 3, and a 2, comma 4. We need these things right here in order for it to be transitive. If any one of those are missing, then it is not transitive. Well, do we have a 2, comma 2? Yeah, it's right there. 2, 3, yes, it's the one we've been playing around with. 2, 4, yes, it's good. So we clearly have all 3 of those. Therefore, this is transitive, right? So that means that one's done. 2, comma 2, 2, comma 3. Let's look at the next set here, 2, comma 4. And I'm going to go through this much more quickly now since we kind of got the big picture here. But again, we have our A, comma B, right? Our A, B is our 2, 4. Well, do we have a B, C? In other words, do we have anything that starts with whatever our B is, which is 4, and comma something else? We have a 4, comma something else. Well, let's take a look and see. And it does not look like we have any. There's nothing that starts with a 4. So in that scenario, this part is not even met. Therefore, it's just vacuously true so far. So far, if the set ended with just 2, 2, 2, 3, 2, 4, and that's all we had, then this thing would be true, right? That's the piece right there that does not exist in this particular scenario. So since our P, in other words, our hypothesis, does not exist, then our conclusion is irrelevant, okay? This makes it vacuously true. And our conclusion being the Q, or the thing on the right of the arrow. All right, so 2, comma 4 works. We would continue checking each ordered pair in this same fashion, and we would find out that all of them will hold up, that this will be true for every one of them. Let's try to remember back to about 20 minutes ago when you did this first set. So this is the first slide I showed you to try to walk through, and then I showed you a second slide, and those are the answers we just walked through. Here's the second slide. Here are the correct answers here for this second set of numbers that you did. Technically, this is the first set of relations you did. The stuff we were just walking through was the second set you did. So take a look here and see if you can make sense of these answers here. Again, I think the reflexive is pretty straightforward. We have the set here, 1, 2, 3, 4, which means there better be a 1, 1, a 2, 2, a 3, 3, and a 4, 4. 1, 1, 2, 2, 3, 3, 4, 4. Bam, it's reflexive. 1, 1, 2, 2, 3, 3, 4, 4. It's reflexive. Easy enough. Symmetric. For it to be symmetric, that means if there's an AB, there must be a BA, right? Well, this one, we've shown that this one's symmetric. There's their A, comma B. So 1, comma 1, is there a BA? In other words, is there a 1, comma 1? Well, yeah, right there. This one, AB, 1, comma 2, is there also a 2, comma 1? Yep, right there. Symmetric, done. This one is also symmetric. Now, I'm not going to walk through every one of them, but you can quickly find, obviously, anytime you have 1, 1, then it's that pair holds that it's symmetric, but we have to check all the pairs. I have a 1, 2, therefore I better have a 2, 1, and I do. I have a 1, 4, therefore there better be a 4, 1, and there is. I have a 2, 2, therefore there should be a 2, 2, yep. 3, 3, therefore there should be a 3, 3. 4, 4, there should be a 4, 4, and sure enough, it holds. None of the other ones will it hold. So, for example, this one is not symmetric because there's a 3, 2, but there's no 2, 3. Antisymmetric. These last three down here are all antisymmetric, which again means that if there's an AB and a BA, then A must equal B. Well, here's an AB, that's a 2, 1. Is there also a 1, 2? No. If there were, then they would have to be, these two values would have to be equal to each other, and since 2 is not equal to 1, this would not be antisymmetric. Okay? So again, there is a 2, 1. Is there a 1, 2? Nope. There's a 3, 1. Is there a 1, 3? Nope. There's a 3, 2. Is there a 2, 3? Nope. There's a 4, 1. Is there a 1, 4? There is not. There's a 4, 2. Is there a 2, 4? No. There's a 4, 3. Is there a 3, 4? No, there is not. So for every one of these pairs, and this condition was never even met. We had an AB, but we never had a BA. So since this was never met, since the hypothesis was false, that means the whole thing is vacuously true, and that held for every one of those pairs. Therefore, antisymmetric, right? Here we go again with this one, 1, 1. Is there also a 1, 1, right? An AB, BA? Yes. Are they? So since these are both true, then are each of those equal to each other? Yeah, 1 does equal 1. Okay, next up, there's a 1, 2. Is there a 2, 1? Nope. There's a 1, 3. Is there a 3, 1? Nope. 1, 4. Is there a 4, 1? No. So on down the line, you'll find that this will hold true where either the pairs are equal to each other, each the A and B, or there is no BA for the pair, like there's no 3, 2 for that 2, 3. Therefore, in the case of the 2, 3, it's vacuously true. In the case of the 2, 2, it's just fully true. And then 3, 4, the last one that is antisymmetric, there's a 3, 4, but there's not a 4, 3, so it's vacuously symmetric, or vacuously antisymmetric. The last three are transitive, but we just walked through those pretty much in depth on the previous slide. So I'm guessing you probably don't want to hear me go rambling on again in that much depth about transitive. Hopefully at this point it's starting to make some sense. If you're a little confused about transitive, go back and watch the previous section of the video about the transitive property, and then make sure you understand it and then try to see if you can apply it and prove it to be true here.